they were digressions. So now see, we had derived the 1D wave equation by argument. Again the same, I will write on this side 1D and this side 3D. So but now I will point out where we had just without thinking we did something. Now you should think and do things. Now see, we wrote, you remember, like this, minus p at x minus dx was equal to, say, rho naught plus rho times, so this is the pressure differential. So now that will be what? So this is like a force, so the acceleration, right, mass times acceleration will be say d, we wrote at that time d square xi by dt square, and we did that, okay. And so now we somehow we are writing in terms of velocities, because we said that displacements are not so powerful to think, velocities are much better. So what we can do is we will write du by dt, right. Now but then am I missing a thing? That no, that's fine. Something is missing, because this okay, if you consider dx must be there, no, because the mass has to come, so this is the density, so this is the length, and unit area we are thinking of, okay, so that it becomes proper. But then here again I wrote the same thing here, what we had written earlier. Second differential of xi I have just replaced with first differential, but then it's not proper. See, the pressure, it's a force, but acceleration should be used, not this one, but because Newton's law cannot handle this, it should be the actual total differential, okay. So it should be, the correct one is this, okay. And when you do that, then you can write rho naught plus rho times, and this you know that du by dt plus u du by dx, right. Now so now you see, so you didn't think about that at that time, this portion. So now see, this term, no, you can write because sometimes you feel like u may be small, but then du by dx also is it small, so you can write this term as this, so that doubt also won't come, right. That term is nothing but this. Now u is small, so obviously this is very small. Then and then when you cannot neglect is, suppose there is a flow of there is a mean flow on which wave is propagating, then this term will be big one. So then you just cannot do with this the way we did, okay. So these are the things which one should note and observe, okay. Then what, so what we will do, I will write this as say dp over dx times dx, I say negative, right? Because from px to px plus x I have subtracted. So that is equal to this. Yeah, so minus rho naught plus rho times du by dt plus half. Okay. So this is one. Yeah. And then dx, I'll erase from here, okay? And that side I don't have even space to write the dx. This dx gets cancelled with this dx. Okay. Then from the equation which we had from here, here, okay. Now think about this f to be the density, okay. We talked about all properties, all types of densities. Let's start with the mass density, okay. So and then for us somehow no mass is getting created. So q is 0 and this is rho naught plus rho, because we are talking about the full density, but rho naught derivative goes to 0, so I can just replace with rho there. Yeah. So I'll write this as d rho over dt is negative of, क्या था वहाँ पे? It was, say we are using this now, so rho naught plus rho times du partial of u with x. So in fact rho naught plus rho times one term somehow, this is the full, no? This is the total derivative, but are we using the total? No, we are writing the partial, isn't it? Have I written somewhere? I haven't written. Okay, so we will use this. Okay, so you will get two terms. One comes to be du over dx, the other is u d. Again here rho naught plus rho will come, but rho naught doesn't change with x, so I can just write with this. Okay. Means again, if you are getting confused with, see this equation, here there is another term, right? So this is like partial Eulerian plus u du df by dx, so that you take that side. So that's what we did here. Okay, but then here there is some problem. Because again, see here we are looking at means in this case also we looked at a particular segment of the tube of one unit area, okay, and then here we said that what is the pressure which is getting applied, but then that pressure at that location is getting applied on the total mass. So here, because Newton's law was getting written, so this had to be the total differential, mass times acceleration. This cannot be the Eulerian. Here we are just seeing, it's completely the what I can say, the Eulerian equation which we are writing, that we are seeing. Let me be more clear why we do that. This is like force is equal to mass times acceleration, okay, and that is why we are using a Lagrangian form here. This is like what do we call, it's like the continuity equation, because the divergence is equal to the rate of change of the property, we are saying. So that is where we are. So I'll say, so this is like, you know, it's like continuity equation. So better to use or easier to use a Eulerian approach. So that's why we use this. Okay, because something is going out, so we think in terms of just that nothing changes. Okay, or whatever comes in, whatever goes out, this is a balance. So this is a balance of mass type. Okay, so that's why the two, here it is partial and there it is total. Okay, now if you remember, we had your P, the small pressure P of the fluctuation was equal to, I think, gamma P naught times that delta, which the condensation, the minus d xi by dx whatever, and that we was, you know, like sorry, rho over rho naught. That was the ratio of that, right, if you remember. So it's the relative change in density. That delta was nothing but relative change in density. So you can go back and see that. So this is the equation which we had written. So from here you can just replace rho with P now. The constants you can take out. So that's the point which I am trying to make. So that instead of writing the equation in the density changes, we are writing in pressure changes, nothing else, by using this gas state equation. Okay. You don't still remember? So this was, if you remember, it was minus gamma P naught d xi by dx, which was the delta, and delta is nothing but the relative change in density. Okay. Okay. Then what? So here we don't have space, so I'll write it here, the full thing. So rho naught by gamma P naught times dp over dt is equal to minus rho naught 1 plus p by gamma, sorry, rho by gamma P naught here, rho by gamma P naught del u by del x minus rho naught basically by gamma P naught u dp by dx. So this is the actual equation which you should use if you don't want to neglect anything. And so from so I wanted to write both the equation at the same place, but somehow, okay, or else I'll write that here. Then you do one thing, from these things you try to see how many types of order of magnitudes are present. Means first order terms, second order term, third order terms. So just try to segregate. I'm just writing it here for completeness. Okay. So see, let me suppose this term, these are constants, forget about them. This and this, these are first order terms. Okay. Now if I multiply this with this, it will be a first order term. But if I multiply this with this, it's a second order term. right? So second order terms are orange. Now here can we see second order, this is a second order term, right? And this will be this is a completely, is it so? Is something wrong maybe? Just check whether this equation is wrong somewhere. I think this was P somewhere, okay?
So that is a rho naught, right?
No, rho naught has come out. So this actually is a P. Just check out. That's why it will become a. Okay. So now this first order term green, right? So this is a first order term. Then this is a second order term. Because P is also small du by dx. And this is also second order term. And then you have a third order term also. Right? So, depending on how much you are willing to sacrifice from the aspects of accuracy, means how important your, suppose speed is very slow, the mean flow, so are you willing to neglect the second order terms, or are you willing to only neglect the third order term, or you have to take all the terms? So based on that you will get the total equations. So these are the full versions, and then we will keep only the first order terms. We have been doing that till now, and okay, in this segment only I'll write the 3D version without writing the full thing. I'm just writing the summary like this, these two equations. The so the equation corresponding to this is d here rho naught by gamma p naught d rho dp, right? dp by dt is equal to minus rho naught 1 plus p over gamma p naught divergence of u minus rho naught over gamma p naught times u dot grad working on p. And corresponding to this, the equation is here there is a mistake, negative gradient. Okay, so in this case, negative gradient of P is equal to rho naught plus rho del u over del t plus u dot grad acting on u. This is the full thing. Okay. So here you should see a term which doesn't look like very familiar, right? Earlier in 1D case it becomes very simple because and here you see this this operation you are having on a vector. Okay, so that's the critical thing. And should I write that? I mean, okay, I'll just tell it. I don't. This expression, if you expand, it will involve a gradient operation on u and a curl operation on u. Okay,
Both will come.
yeah, both will come from this if you expand this. So now it depends on whether your fluid is irrotational or something. So those terms either you can or you cannot neglect.
Curl we can
Huh. So all those things are hidden inside this term also, the curl part. Whether some circulation is involved in the flow. Okay. Yeah, you're writing that. Okay. So now what we will do, and then further for this course we will neglect all the second and third order terms. Only the first orders we will keep. And okay, just this was to show you that if you wish at any point of time you can use these things. So I'll come back to this page if you wish to write. And finally, what again I am skipping. Okay, I'll write it. So dp over dx negative gradient is minus rho naught del u over del t. This is the first. This equations when you keep only the first order terms, and then so I'll write both the first 1D and 3D there. So 1 over gamma p naught times del p over del t is negative d over dx. And from them you can actually calculate the one which we had derived. And for 3D you just have this is the one, then here this one, and from there again you are getting I'll write in the same way. Okay. So so these are the equations, and again to remind you, same thing is happening. If you are differentiating a scalar with respect to a coordinate, just replace with gradient. Vector with time doesn't make any difference. Vector's component with coordinate, divergence, yeah, and Laplacian is Laplacian. So, okay, and here you should be comfortable also with respect to the meaning of the Laplacian, because whenever you see such equation, how do you visualize Laplacians? In 1D, this is the curvature, right? Suppose this is in terms of geometry if you think, and so this one is like a curve, you will get a curve, and then the curvature is represented by this. And if you go to 2D, that will give you a bump type of thing, bulge, means in 1D you will have this kind of curve, in 2D you will have bulges somehow like that, means anywhere Laplacian, if it is not 0, that means it is having a curvature there. Okay, and in 1D you should use the word curvature, in 2D you can use the word say bumpiness or bulginess, somewhere it's bulging. And what about 3D? In 3D, huh? You can use the word lumpiness. Something lumps somewhere.
Increased density.
Yep, means anything. Concentration changes. So means and positive Laplacian's positive value means net flow will go out. Okay, so that's the meaning of positive Laplacian. So okay, so the system will try to reduce that now going out. So curviness, bulginess and lumpiness are the geometrical thing which the Laplacian represents, and whenever those things come, no, something will happen, means something will start to move basically anytime, and it's a general statement that mean anytime when you see the one more interpretation of the Laplacian, actually from there you can calculate also, is that the actual value is different than the average. This is the average value. Actual value is different than that. Now this difference actually is being represented by the Laplacian, and so if things are flat, even there is a slope, always there is no tendency of movement to start, because people will think, suppose in society also, if you think that richer people are there, poorer people are there, I am on the average, no force. But then this difference of average than average will create any movement. So that's why, and suppose Laplacian equation when you write, what is the meaning of that? Laplacian is 0, right? So that means anywhere in the domain you cannot have a maximum minima. That's the meaning. You cannot have a bulge because it's 0. If there is no bulge, so there cannot be any maximum minima. It has to be a flat thing. Okay. So in 3D, if somebody is saying that Laplacian is 0, that means there is a gradient of the concentration, but it is so linear that nothing is changing now. It's a flat in 3D. Okay. Okay. So yeah. So that you should. So in 3 types of equation you have seen, right? So this side is that curviness which is represented. This side 0 is the Laplacian equation. This side the first derivative, your heat equation you write, and second derivative wave equation. So these are the 3 class of basically equations which we deal with. This side being the I would say forcing effect. Okay. In fact, if you just not related to this, curvature of space-time is gravity, right?
Yes.
That's the thing. So there also exactly same equations will come. Space-time's curvature will create force. So it's a general principle in nature. Okay. Okay, we'll stop for this segment.